All right, so today we're going to finish up with arrays, with just a bunch of miscellaneous stuff that you should be made aware of. A little bit deeper on how arrays work with respect to memory and stuff like that. So the first thing I want to address is who owns memory, right? And you might have seen this. This question might have come up in your lab yesterday on when do you free something, right? So, for example, in the first exercise, when there was an intentional memory leak, right? We had this function that created a temporary copy of another array. It operated on it, it sorted it, it did whatever it needed to do. It found the median, and then it was done with it, right? When that function returned, there was no way for anybody else to clean up its mess, right? So, if a function creates temporary memory that it uses to process data, it owns it. It is responsible for cleaning it up, right? Cleaning it up, right? Basically, whoever owns the memory is responsible for it. If a function returns a chunk of memory, or an array or whatever, right? Then the calling, it is transferring ownership to the calling function. And for an example of that, transferring to ours, there we go. We'll just go back over here to what we were playing with on Monday, right? So for example, get counting array. When we created this array, right, we returned it, right? If this function were responsible for cleaning up that array, what would it look like? Before we return, we want to make sure that we clean up. Free array. Now, does that make any sense? I'm creating something, I'm populating on line 23, I'm populating it 24 through 26, and then I destroy it. Can I return something that I've just destroyed? Nope. So it's not responsible. This function is not responsible for cleaning up after itself. It is creating this array and then returning it. Whoever calls this function implicitly takes on ownership of this array. Down here in main, when we called that, is it weird array? Yeah, we called it weird array here, right? Did we ever use it after that? Looks like we printed it out, right? So we're done with it at this point. The very second that we're done with it, that's when we free it up. Weird array. All right. If I didn't do that, what kind of message would I get from Valgrind? CSCE 155H, GCC. What's the flag that I need to use Valgrind again? G, right? Demo.c. Right. And by the way, I should be using the WAL flag, right? A good chunk of mistakes could have been found by simply using the wall flag. For example, the second exercise, where you had to fix returning a static array, you had to change that into a dynamic array. The wall flag would have been screaming out to you what was wrong, right? So let's go ahead and run this, right? It runs just fine. If I run this through Valgrind though, a.out, I see a lot of memory leaks here. Definitely lost, 48 bytes in 2 different blocks, right? That's the heap. This is a heap summary of various chunks of memory here are lost. Well, one of those is the weird array, right? Another of those is the only evens array, all right? And once I'm done with that, I should free that up, only evens. If I need to use those, of course, down here, right, I can't have access to them. If I've destroyed it, then I should not be able to expect to do anything with it. For example, if I tried to print out the first element after I've already destroyed it, 0, only evens, sub 0. Right. There we go. Let's try that first before we do our memory leak. GCC. If I just run this, hopefully, oh, nope, it doesn't even manifest itself as a mistake. It works on my computer, but it doesn't work on the grader, right? Well, that's because you've got a hidden value here that is being corrupted. In fact, look at that. You can see that it's corrupted, right? It doesn't result in a segmentation fault, but is that, well, that's certainly an even number, but was that in the original? Nope. In fact, it's been corrupted right here, right? So what we need to do is make sure that we're not accessing memory after we've freed it up. Only evens. Oh, you know what? I wasn't done with weird array, was I? I gave it the weird array to this one over here, and so I should only free it up down here at the bottom. That's why it was corrupting it here as well, right here. Right? So GCC, if I run this, it looks fine. Run it through Valgrind, and now I get 0 errors, 0 context, and the best message of all, no leaks are possible. Right? You've stopped up all those leaks. But you only were able to do it if you do it in the right spot. Right? So if it transfers ownership to the calling function, that function is then responsible for it. Right? Generally, if you have memory that is allocated in, or that is owned, I'll say, by main, you can kinda, and I'll just kinda sorta get away, there we go, get away without cleaning it up, right? For example, in this example that I just did, right? I clean up my memory and then the program ends, right? Well, when the program ends, the memory will be cleaned up by the operating system anyway, right? Everything that's ever been allocated to the program will come back to the operating system. And so you really don't need to do this, strictly speaking, right? It's just, shut off the lights on your way out, right? If you want to, put it there. What is different, an exception to this is if you're writing like a real application that's intended for a long-running process, like a web browser, or a server or something like that. You make sure that you free up all memory everywhere all the time, right? Why? Because if you have a memory leak and it's running for weeks at a time, eventually it will grind to a halt. Right? These are ephemeral programs that execute in a matter of a blink of an eye. Right? They're short-lived programs. So who cares, right? But definitely clean up inside of functions if they have temporary memory space, okay? So that's who owns memory. How does memory actually work, right? Why do we use 0 indexing, or I'll write it like this, 0 indexing in arrays, right? So if you were to ask a grade schooler to start counting, where would they usually start counting? Oh no? 1, why, right? Those are the counting numbers, 1, 2, 3, 4. But then you get into, I don't know, middle school, high school, and you learn that those aren't the counting numbers. The counting numbers start where? Or hopefully we do. The natural numbers? Oh, we've seen this before? Like the natural numbers, they start where? At 0, 1, 2. Why? Because in real math, you need an additive identity, right? You need a 0 in order to, to start building more complex things like the integers, negative values, right? You need an additive identity here where if something that added to any other number in the natural numbers gives you that number back. X plus 0 is X, right? That forms the basis of algebraic systems with various, properties, rings, semigroups, groups, fields, stuff like that, right? That you probably don't get into in high school, but you implicitly do by starting to talk about these more complex number systems, right? So mathematically, it's more mature, but we do it for a different reason, right? We do it because arrays are actually memory addresses, right? And we've seen that implicitly here. So let's come down here, and how do I represent an array again? A pointer. Right? What is a pointer? A memory address. When I go and I index it, there's some magic happening under the hood here, right? Indices, indexes are actually memory offsets from the beginning of the array, right? The array name, the array variable name, is a memory address that starts at the beginning of the array, right? The next element is a certain number of bytes over right? Offset, right? So for example, if I had, say we have an array named ARR, right? Then the first element that we know of right now as ARR sub 0 is at memory location ARR, right? The second element, again, which we know of as ARR sub 1, is at memory location ARR plus 4. In other words, 4 bytes over for an integer. Say we have an integer array. If this were a double array, doubles are 8 bits or 8 bytes, and so it would be 8 bytes over. This is a memory address. 4 bytes over is another memory address. Where do you think that the third element would be? ARR sub 2, the third element is at memory location what? ARR plus. So 0 over is the first one, 4 over is the second one, 4 over again is the third one, plus 8, right? Let's take a look at a visualization of this. There we go. So if I've got an array here with 2, 3, 5, 7, the classic prime numbers here, when you write ARR sub 0 here, behind the scenes it's doing some math. It's taking this memory location and the index, and it's multiplying the index by the number of bytes that an integer takes, which in this case is going to be 4. 0 times 4 is 0, so we get the value ARR sub 0, ARR plus 0. In other words, it points to right at the beginning of the array. 2 takes 4 bytes to represent, because all integers take 4 bytes to represent. So the next one over is 4 bytes over. And the way that that happens, again, it's just math. It's going on under the hood. ARR sub 1 is equal to ARR plus 1 times size of int, which is going to be 4 bytes here, and that gives you ARR sub plus 4. Right? Plus 8, plus 12, plus 16, etc., etc. This entire process is called pointer arithmetic. You could do the second part here in your code if you really wanted to. In fact, there are situations in which you have to do that, right? Generic programming, where you're given an array and you don't know what the hell is in it, right? You don't care, right? For example, you want to sort it. And if each element is 4 bytes and 4 bytes, 4 bytes, 4 bytes, or whatever, and you want to sort it because these two things are out of order, all you need to know is I need to take these 4 bytes and these 4 bytes and swap them, right? I don't need to know what the hell is stored in there. Right? I just need to know how many bytes they are, right? If I want to swap them around. And if you want to write one, say, sorting function to rule them all, to do anything, any sorting of anything, right, then you need to make it generic. You would end up having to do some pointer arithmetic like this. Fortunately, we don't have to do that. We've got the syntactic sugar built into every programming language now, where you don't have to think about the pointer arithmetic that's going on under the hood, right? Nice. But now we understand why we start our indices at 0, because it's a memory offset. And where is the first element? It's 0 bytes away from the start of the array. It's right here. Imagine if we started our counting at 1, right? What is that? The counting numbers. I don't even think that has a... that's not really even a set that usually people talk about. Like, I guess mathematically you would say that it's n positive, right? Only the positive numbers. So in other words, you're excluding 0 now, right? So if we were to start at 1, 2, 3, 4 because it's more natural to us humans, right? Then it means that that under the hood they would have to do the math different. They could do that, but it also means that, or if it's not doing the math under the hood like that, it means that you always have to burn 4 bytes at the beginning, right? So this is I'm not saying that one way is better or versus another, but this is why it is what it is, and every language does this now, whether or not it's actually memory addressing and stuff like that or not. Right? What are the exceptions that we've talked about before that you might know? There are a dozen programming languages or so that use one indexing. Does anybody remember what one of them was? No? Does anybody I thought somebody did Roblox programming? Yes? No? Lua is one. Nobody had any Scratch in like middle school, grade school, high school? Scratch? It's a visual programming language, right? No? Okay, never mind. It starts at 1 as well. And then the other one that I know of would be MATLAB. And those are the 3 big ones that lots of people would be familiar with. But nobody's familiar with any of those? Okay. I thought everybody did Scratch in like grade school now, right? No? Okay. Weird. All right. So another aspect of memory is sometimes you will have to discern between what's called a shallow copy versus what's called a deep copy, right? So take a look at this following example, right? A shallow copy. So I'm going to go over here to Python tutor, and I've already set this up, okay? What I've done here on line 4 through 7 is I've created an array of size 5, and I've populated it with values 0, 10, 20, 30, and 40. So if I race through this, there we go, not too far, there we go, 10, 0, 10, 20, 30, 40. That array, the pointer, is pointing to the beginning of the array, right? 0, 1, 2, 10, 20, 30, 40, 50. Now let's go ahead and go down here to 9. I'm about to make BRR, right? Why? Burr, it's just the next one, right? ARR, array, Burr, it's the B array, right? So I'm going to make that point to array. Visually, what's that going to look like? I'm going to have 2 arrows pointing to the exact same thing. Right? This is what's known as a shallow copy. I've got 2 references that reference the same thing. Now, when I change the first element of BRR to 42, tell me, from the perspective of ARR, is anything going to be changed? ARR points to the array, right? And 42 is there, right? Here, let's go ahead and prove it. Let's go ahead and print f. ARR sub 0 is equal to %d and line array sub 0. Right. Visualize this execution. Right. And I will simply race to the end here, right, and see that it actually outputs 42. Right. Why? Because they're referencing the same thing. It's shallow, right? It's not that we have 2 references, but they're referencing the same thing. Changes to one are affected by the other, right? And this should actually be expected because this is exactly the point of the swap demo that I gave, right? If I've got a pointer to one thing, I can change its contents. If something else is observing that pointer, or that whatever that pointer points to, then any changes through one pointer are reflected by the other pointer, right? Consequently, this is known as a shallow copy, right? A shallow copy is when you have more than one reference to the same thing, array, right? Changes to the array are reflected in both references, right? Okay? Sometimes we don't want that, right? Sometimes I do want a completely separate copy so that you don't go mucking up my data. You saw that yesterday in your lab, right? When you wanted to compute the median, we handed it off to this function. To compute the median, to find the median, it sorted it. We didn't want to sort the original, so we made what's called a deep copy, right? A deep copy is a completely separate copy of the thing, of an array. I'll just say that it's arrays, right? It can be more than arrays. Anything that is in memory, you can make a deep copy of it, right? So let's come over here to our array demo, right? And let's think about how we can make a completely new deep copy, right? So for example, let's go ahead and go with int. Do I have primes in here already? Yes, I do. Okay, they're primes, right? So let's go ahead and say copy int star copy of primes, right, is equal to primes. There we go. This would be a shallow copy. Maybe bad, maybe not, right? It depends on your use case. Are you going to be making, do you want to make changes to it? If so, then fine, a shallow copy is good enough. But if you don't want changes to be made to your data, you want to have a bunch of data, you want to process it, but you want to make sure that you retain the original copy, right? That means that you need to make a completely different clone, a completely different deep copy, operate on that copy over here, right? And then leave the original data alone. Right? So what I want to do is, let's make a deep copy instead. How would I go about doing that? Well, if it's a completely new and separate array, what do I need to do first? Allocate memory for it, right? Copy of primes is going to be a call to malloc, star malloc. How big do you want it? As big as the original, right? In this case, what was it, n I used? Yep, n is 8 times size of int. There we go. Now, does that copy everything over? Nope, it just creates a new array, right? What I need to do now is I need to go through each element and copy it over. For int I equals 0, I is less than n, I plus plus. Copy of primes of I is equal to primes of I. There we go. And now that's a completely new deep copy. What would that look like over here in Python Tutor? So let's not make a shallow copy here. What we'll do is copy what we just did. That we're going to make a new copy of size n, and then BRR is going to take on the value in ARR. So that when I change 42 here, what would my expectation on the original array be now? Let's visualize this. Come on, there we go. Right. Next. I've filled up the first array. I'm creating a completely separate array. So now instead of having two arrows pointing to the same thing, two arrows are going to be pointing to completely different things. I copy over the elements. And now changes to one are not reflected in the other. BRR of 42, that doesn't change A. It only changes B. Print it out, and you see that it's still 0 up here. Right? Gee, that sounds so useful. Maybe I should do what? Put it in a function, right? And we gave you that function yesterday in your lab. If you want to copy that function and use that function, absolutely, please do so, right? We give you code for a reason, right? All right. In fact, let me go ahead and write it over here. All right. You can easily write a deep copy function for common arrays. In fact, if you don't want to write your own, you can use memcpy. Okay. So what do you think that stands for? Mem is short for memory. CPY is short for copy, right? So what would that look like? memcpy. Right? If you want to use this, you're more than welcome. You're going to have to learn how to use it though, because I'm not going to cover it in detail here. We've got a destination, we've got a source, and we've got the number of bytes you want to copy over, right? Here's a chunk of memory, here's a chunk of memory. I want you to copy n bytes from this chunk of memory over here to this chunk of memory over here. That does not, or source to destination. Note that it's backwards there, right? It's the source is going to the destination. Why? Because if you wrote x is equal to 42, right? You're taking the thing on the right-hand side and putting it in the thing on the left-hand side. And that's why the source is on the right and the destination is on the left. It's following that same pattern, right? What would that look like over here? Let's see, in our code here. You still need to set up the memory, right? You still need to call malloc. It's not going to set up the memory for you, right? It's going to assume that the source and the destination are valid memory. This is a pointer to the destination of the array where the content is to be copied, typecasted to a pointer type void. And it is going to all right, Yeah, it's not. It doesn't say it explicitly here, but it's going to assume that destination is big enough to hold whatever you're trying to copy. Right? That's on you, right? If it's not. So I've created enough memory here, certainly. Now I can go mmcpy of copy of primes, and how many bytes do you want to copy here? Do I just want to copy n bytes? Now remember that there are, n here is 8. That's the size of the array. Oops, too far. That's the size of the array, right? Each one of those integers in that array takes how many bytes? Size of int. So you need to use it like you do with malloc. Right? Let me show you what that looks like over here. Ooh, I don't know if it's going to be this sophisticated enough to do this. Let's copy it into burr. R. Please do it. Please have mem copy. Okay, yeah. Please work now. There we go. Set up the memory, so it's pointing to this. memcpy, it's going to do it all at once. No for loop here at all. Oh, hey, cool. It did work. So memcpy is another tool that you can use if you don't want to write loops to do stuff, right? All right. Questions so far? All right, then how do we do all this stuff? Again, this is a visualization. I thought the Python tutor was a little bit better than this. All right, this is a shallow copy where B is pointing to A is pointing to the original, and so therefore B is pointing to that. Changes to one are affect both, but a deep copy is a completely different copy of the memory address, so that changes to one are not affected by the other. Right? I like Python tutor better. Right? Okay. What about these concepts in Java? Let's start up here again. Who owns memory in Java? Java owns the memory, right? The Java virtual machine is responsible for all of this stuff. Do you need to worry about ownership, that this function is creating temporary workspace and therefore it needs to be cleaned up? Nope. Java takes care of all of it for you. The Java virtual machine does. It has automated garbage collection. How does array memory work? Under the hood, it's exactly like this. Right? The indices that you use are syntactically exactly the same, and therefore it is doing basically a memory offset. Right? Shallow versus deep copies. I wonder. Right? So let's go with lists instead here, right? Because I don't want you using arrays unless you have to in Java for whatever reason. Numbers is equal to new array list. And let's go ahead and add some numbers. Dot add 10, 20, 30, 40, 50. There we go. Cool. System.out.println numbers. Here's a shallow copy. List of integers. Right. Foo is equal to numbers. I have two variables that refer to the same list. If I print these out, in fact, I'll wait to print them out down here. Right? Print out numbers, print out foo. You see that they're going to be exactly the same. 10, 20, 30, 40, 50. But when I make a change to one, say foo dot, I don't know, replace, not replace all, dot add, let's just go to add 60. There we go. Print both of them out again. Will 60 be part of both lists or just one list? Remember, this is a shallow copy. Changes to one are reflected by the other. So therefore, both of them will have 60 in it. Right? What about a deep copy? Foo should be a copy of list, of numbers. That means, if we're going to do this traditionally, new array list. There we go. A completely brand new array list here. And for each element integer x in the collection numbers, we'll go ahead and add it. foo.add x. There we go. There's a deep copy. Now, 60 was still in there, by the way. So let's go ahead and print them out again. Make sure that they are completely different copies. In fact, let's put out a delimiter here. There we go, so that we can see them. Now I'm going to go ahead and change foo. foo.add 70 instead. Now, because this is a deep copy, changes to one are not reflected by the other, and only foo will now have that 70. The other one will be unaffected. They were both 10 through 60 before, 10 through 60 before. The original is still only 10 through 60 because I am only making changes to this to the second one. There must be a better way. There is. Deep copy via a copy constructor. So we're not going to get into object-oriented programming too deeply in this course. That's for next course. But when you construct a new list, that's what you're doing right here. This is actually calling a function. It's calling a method to construct that object, to construct that new list. The way that I've been using it up to this point, say on line 32, I've not been passing anything to this constructor. That's going to change now. What I'm going to do is foo is equal to, here, let's go with a completely new list integer. Let's go with bar is equal to new array list. Now, instead of leaving that blank, I'm going to pass in another list here. Let's say numbers. Right, there we go. And print out bar. What that's going to do is it's going to construct a new list with a completely new and deep copy of the numbers in that other list. So there's bar at the end, right? 10 through 60. So just like memcopy, yes, you have some facilities here to do deep copies. What about arrays? Deep copies of arrays. Right? Let me go ahead and create an array here. Int primes is equal to 2, 3, 5, 7, 11, 13, 17, 19. There we go. I want int copy, deep copy of primes is equal to, there is no memcpy in Java, right? Why? Because you don't have any memory management. But there is a whole collection of array utilities. Oops, that's not what I wanted. Arrays dot. Hey, look at all these functions that you can use, right? You've got dozens and dozens and dozens of functions here that perform basic operations on arrays, including, hey, copy of range, copy of, right? There we go. Copy of Boolean, for Boolean arrays, for byte arrays, for character arrays, for doubles, et cetera, et cetera, et cetera. Let's go ahead and we'll go with copy of, I want primes, right? Now it's going to complain here, array, why are you complaining? All right, it's in java.utils. Import it. Now it's going to complain for the reason that I thought it would complain, is let's hover over this and read the documentation for this. Oh, come on. All right, fine. I'm just going to put in a temporary number here so that it, what? Come on. Copy of, you should be taking an argument, right? Add arguments. There, okay. Whoa, okay. We need to look up the documentation here. Java arrays, copy of. There we go. Nope, I don't want that. I want Java docs. There we go. All right, find copy of. There we go. There's the original. So if I want a copy of something, where is the integer version? Here we go. You give me the original integer array and a new length. So in other words, what this utility here is actually more general than just memcopy. Memcopy, you want to copy over just this chunk of memory. Tell me how big it is. This one will actually give you different behavior. Let's read all about it. it copies the specified array, truncating or padding with zeros if necessary, so that the copy has the specified length. In other words, if you had 10 elements in the original, and you said, I want a deep copy, but I want it to be of size 20, it will copy over the first 10 elements, and then it'll pad it out with 10 more zeros. It'll make it bigger for you. Right? If you say that I've got, the original has 10 values, but I only want a copy of the first 5 values. Right? Okay, I'll only go ahead and create a brand new array of size 5, and I will only copy over the first 5 values. Right? This should, deep copy of primes, no. Oh, duh, that's why. There we go. And I want, if I would just want an exact copy, primes.length gives you the size of the original. Right? If you want, I don't want the first 8 primes, I want the first 4 primes. Subtract off 4. I want an array of size 10, add 2. Right? Now it'll have 2 through 19 with 2 zeros at the end. Let me show you. System.out.println, deep copy of primes. Don't want to type that. There we go. Run it. Uh-oh. What is that thing? Not memory corruption, right? You would have to bend over backwards and do some somersaults in order to get to try to get memory corruption in a Java virtual machine. Right? So what is that? Does anybody know? Yeah.
When you try and print just an array, it gives you the memory address.
Exactly. You're getting the memory address of where that array is stored, right? I thought we didn't have memory management. No, we don't. You can't do anything with it, right? You can print it out and say, oh, well, fabulous, it's at that memory location. It'll always be at that memory location because Java Virtual Machine is deterministic. So, okay, fine. Is there no way that I can nicely, print something? Well, like I said, you've got dozens and dozens and dozens of utilities here in this arrays class. Maybe you have some sort of a toString method. There we go. You give me your array, and I will nicely format it as a string so that you can print it out. And hey, there are those 2 extra zeros there, because I copied over the original length plus 2 at the end here. Neat. Oh, sorry, I've been neglecting online questions here. I don't know if this is an actual person in the class. Is this JavaScript or C++? It is neither. This is Python? No, this is not Python. Right. Okay, never mind. Just random internet folks. All right, any questions on this so far? No? All right. So I will make sure that you've got at least this code here in your notes at the end. And the takeaway here is, yes, you have arrays in Java. In fact, on your hack, you're going to have to deal with 2-dimensional arrays in Java because that's how we represented an image. You're going to take an image and you're going to flip it, mirror image. You're going to flip it horizontally, vertically. You're going to rotate it. And I think that those are the only 3 things that you have to do. But you have to manipulate 2-dimensional arrays like that, right? Both in C and Java. So looking ahead here, Friday, I will give you a demonstration of GDB because when we come back on Wednesday that week, that's the midterm, right? All right, that's the midterm. Since we're covering GDB on that Friday, what I was thinking of doing, and feel free to make other alternative suggestions, but the midterm is going to be opened up again like 9 a.m. or something like that, maybe even earlier, whatever. Any early birds? All right, so what time would you like it to be open in the morning? 5? Okay. I could just do midnight if anybody's a late person the night previously or something and give you 24 full hours. That's fine with me. The first one went so well that there was only one incident in a completely different class in which we suspected that something was going on. Otherwise, everybody did well. So 24 hours on Wednesday you'll have. Since if you choose, you can go ahead and use this class time to do the midterm, right? But what I'll do since I have to be here anyway, no matter what, I will use Wednesday's time for a review during the midterm if you want. And for that reason, it's completely optional. I mean, I don't take attendance in this class anyway, but if you want to come, watch the review. If you want to instead, watch it, live stream it or something, if you want to ignore it entirely and use that time for your midterm instead, that's fine too, right? Sound good? Okay, same as before, open book, open note, open computer. Do not post anything to Piazza, do not post any code to Piazza. You can post questions, of course, to Piazza. Don't share code, don't even talk to anybody else in this class or outside the class for that midterm. It has to be completely 100% your own work. It is worth 100 points. Had I to do it over again, I would probably make it worth only 50. Expect it to be the length of the first exam. It's not going to be like double the length because it's worth double the points. Right. No questions? Okay, then I'll see you on Friday.